Dear participants of micro irrigation engineering subject, we are starting a new lecture on soil water movement under drip emitter. This lecture is in the serial order. This is 35th number lecture, and we have been dealing in previous lectures about the hardware part of the drip irrigation system, its installation, its operation, maintenance, and then we also discussed different types of emission devices. So, dripper is one of the emission device. When we are talking about the soil water process and particularly with a drip emitter. So, we will learn about the theory of water movement through drip emitters, and when the drip emitter it is water is flowing through the soil considering steady state conditions or it is a unsteady state condition. So, we require information that how the soil moisture is moving when the water is being applied through a drip emitter, which is of different application rates. So, different application rate we know that in case of drip irrigation system, the water is coming out in the order of 1 liter per hour, 2 liter per hour, 4 liter per hour, 6 liter per hour. So, how it is moving in the soil, and so in the lateral direction or in the vertical direction. So, purpose is to weight the root zone of the crop, effective root zone of the crop, but water movement it takes its own shape. So, time of application and then this and as well as the discharge, this is important, and when we want to decide a spacing between the drip emitters in the lateral pipeline and spacing of laterals, or we can say spacing of drip emitter in the the laterals. So, lateral to lateral spacing and plant to plant spacing, this matters when we are designing the drip system. So, water applied from a dripper may be considered as a small circular point sources, symmetry is spread in all directions. Symmetrically it is spreading in all the directions. So, it ideally it should be a circular, but it will depend upon the soil texture. So, when water is being applied, there is a infiltration infiltration takes place, and this movement of water it is a 3-dimensional in nature, and means with respect to the 3 space coordinate, that is x, y and then z direction, that is the vertically downward direction. Each emitter can be considered as a independent unit, weighting the soil volume without having any interaction with the neighboring emitter when we are considering individual. So, when they are sufficiently spaced, but when we are designing, once we know for one particular dripper, we will consider this same spread will be there in the another dripper, then what should be the overlap, so that the uniform depth of water it is given beneath the soil. The physical process involved in case of drip irrigation system when the water movement takes place, say irrigation system when the water is we are giving, this is a case of unsaturated flow, except when the water initially when water will flow. So, movement will take place only when it is in a saturated condition, but in irrigation process you will find that the it is unsaturated flow. So, we are considering the water flow under a drip trickle irrigation is the essentially 3 dimensional, it is a saturated and unsaturated flow problem with moving boundary separating the ponded and unsaturated area of the soil surface. Now, the emission point of drip emitter, it is observed that the radial area of ponded water develops in the vicinity of the emitter source. This area is initially very small, but radius becomes large as the time increases. Means when we keep on supplying water with the help of dripper, then the water will spread, it will spread horizontally above the land surface. The effect of storage as the soil water surface is negligible, as the ponded body of the water is usually very thin. This implies instantaneous water infiltration into the soil and evaporation to the air. That is a physical process, it is taking place. Now, you can see here a dripper is being used, and now we are supplying water, when we are supplying water, what will happen? The water will there will be ponding, of water, and there will be thin layer of ponding of water, and then water will spread in this direction, that this is your radial direction, this kind of a thing, it will be radial flow. So, this is this particular place where the ponding takes place, this is the radius of saturated water zone. Now, when we supply water, naturally there will be evaporation from the surface, that is from the soil surface, and also transpiration will take place from the by the plant body or plant surface. So, transpiration and evaporation, of course, from this particular area where the shading takes place. So, this becomes, as long as it is not open surface. So, these two components are put together, and that we call it as a evapotranspiration, but when it is not affected. So, from the open surface evaporation will take place. Now, when we continue to supply water, you may find that the wetting bulb it forms. This is the wetting bulb, and as we continue, then the wetting bulb will continue to develop, and this is the way we are seeing that this is the continuous. Now, we consider when we are making theoretical analysis, that is the. So, we consider that this particular dotted line area, it is a this is the boundary which we call it as a control volume. This is a control surface or control volume, where we take it that, and then the water beyond this particular control volume means there is no flux, means water from this area, means water or from this part to this part, no water transport takes place. So, this is the ultimate when you have taken this particular boundary, when we are considering, this is your ultimate total radius of saturation. So, soil water content immediately beneath, when the water is being given, the soil water content beneath the ponded area is always equal to the water content at saturation. Since this saturated place is only place where the water can infiltrate into the soil, and we refer this area as a zone of saturated water entry. So, this part which is being told that this part is known as a zone of saturated entry, and this is the radius part. Now, a very simplified equation, if someone wants to know without going to the typical analytical process of the water movement, then one can simply put it a simple relationship of the infiltration. So, where suppose when water is being given, into through the drip system, naturally it is weighting the soil. So, moisture content at when it is being, if we are measuring the soil water content after the irrigation has been given, that moisture content and shape of weighting volume is taken as a hemispherical. So, initial moisture content, that is your theta dry, and then the moisture content in the after the irrigation has been given. So, difference in soil moisture content multiplied by this particular volume of the hemisphere can be given by the total amount of water supplied by the drip emitter. So, total amount of water supplied by the drip emitter is nothing but the discharge rate multiplied by the time of application. Now, this is the volume is equal to this particular volume, that is a 2 by 3 pi R f. R f is the weighted volume, or we can say weighting front position. So, this is the thing which can be expressed. This is a simple form. Someone wants to know that yes, what will be the volume of the weighting. Now, soil water movement through drip system, one can consider different cases. So, one case is then when the water from the point source, means dripper, when the water is coming from a dripper which is kept on this above the land surface, and then water is coming drop by drop when it is falling. This is a point source system. This particular thing which you see here, this is a point source emission system, and then water is being coming drop by drop, and then it is a forming the case. Now, so this particular case we are considering that it is a one case is taken as a steady state case. Now, when we are considering that the surface ponding takes place, that is another way of that, where the how much the water which is going as a surface ponding, and then line source means when the drippers are kept, it is inline drippers, particularly in inline dripper, it forms very small strip of weighting of the land surface. So, it is normally it is put up below the soil surface, we call it as a buried drippers. And then this means here we are considering as if the flow process means the change in the soil moisture content is independent of time, but here we are considering in transient case that as if the moisture content it changes with time, and this is means this is for unsteady state case. Another one is it is not the function of time. When we say steady state case, this is not the function of time. So, these three cases are considered when delta theta by delta t is considered as a 0. Here delta theta by delta t, it has relationship with movement of water. Now, subsurface water soil water regime for high frequency irrigation. This is a drip case. In drip irrigation system, we call it as a high frequency irrigation. So, subsurface soil water regime is determined by properties of the soil and geometry, means what is the geometry of the flow which is taking place, and rate of water application and withdrawal from the profile. So, factors that differentiate the soil water regime for micro irrigation from standard surface and sprinkler irrigation systems are how they are different. That is how it is explained here. The flow regime, in case of high frequency irrigation, flow regime is considered as a 2 or 3 dimensional rather than only vertical. If it is a say if it is a sprinkler irrigation system, it is a surface irrigation system, there is only vertical movement of water it takes place. But when we are talking about the the point source irrigation system or line source irrigation system, then it is a case of not only the vertical movement, but water takes place in the horizontal or radial flow as well as the vertical downward movement. Water is added at high frequencies, means here water is being given daily, or sometime you may find 2 times in a day. If it is a small quantity of water is to be given, then 2 times of this. This is a high frequency irrigation. This is the another characteristics of micro irrigation system, and then soil water content is maintained within the relatively narrow range. So, the multidimensional nature of flow from point or line source lead to more complex mathematics if the system is modeled. So, high frequency of application and narrow water content tend to skew the concept of field capacity, where soil properties control plant available soil water. We are very of course, these informations are important, and particularly in case of the irrigation process, we deal with the metric water potential, we deal with the unsaturated soil water content. So, there exists a relationship between the pressure held and soil water content. Okay. So, H is greater or near atmospheric pressure, the system will be near saturation, means this is for the saturated flow case. Okay. So, that is one part. Now, H is less than atmospheric pressure. So, the water content also decreases, and then H will decrease. So, we call it as a soil water tension, and then water retained. If we measure the how much is the water means the pressure available which is held by the soil particle, we call it as a soil water tension or metric potential. So, there exists a relationship between the soil water content, that is your theta, with H, that is the metric potential. So, this particular relationship when we draw, we call it as a soil water retention curve, or this curve is also known as soil moisture characteristic curve. So, soil moisture characteristic curve means H equal to 0. When we say H equal to 0, means soil is perfectly wet condition. Wetting condition means it is at the soil is at the wetting condition, means it is the saturation condition. And as the means when we are talking about this part, that is the negative part, means when the water content is decreasing. So, H proceed along the negative axis, the theta decreases monotonically. Now, this is the another this is the part when we are putting it H versus theta, means this is your moisture content, and that is explained that how the H versus theta it changes. Now, a soil water characteristic curve may be obtained by taking initial saturation sample and applying the suction or pressure to desaturate, or simply when we say desaturation or drying process, simply if you say that this is the drying process. So, when the soil water start decreasing, the soil water tension will increase, and this particular R. So, this is a desorption process. Gradually, when soil is dry and we are giving water, means we are irrigating. So, irrigation process is when we say that gradually wetting an initial dry soil, that is a sorption. So, this curve is sorption, and sorption means we are adding water in a dry soil and moisture content of the soil increases, and this particular curve is when it is water is being withdrawn from the soil, when you are using a means apparatus, that apparatus you are withdrawing water from the soil, and that particular withdrawal is that particular process is known as a desorption. So, these two pathways produce the curve, and the most cases are not, these two cases you can see here, these curves are not identical. So, this means this process when we are drying, this is known as a hysteresis. This is known as the capillary hysteresis curve. Now, many algebraic equations have been introduced in order to model the soil water characteristic curve. So, these are the two famous, one is the Van Gunsten model, another one is Brooks and Corey model, and they have established the relationship, and their relationship is given here. So, here in this particular thing what you see, this is the relationship that K by Ks, this particular ratio K by Ks, that is which is known as the ratio of the hydraulic conductivity. One is your K is a function of theta, another one is saturated hydraulic conductivity, that can be related by this equation, where m is the one parameter, m is parameter, and theta Vg, alpha Vg, that alpha is the parameter which is coming here, which is function of Se, that is your the effective saturation. Effective saturation is given by this expression, where alpha Vg is, this is also soil parameter, and that is Vg, when we say that is the Van Gunsten parameter of the soil, and so m, n and alpha, these are the, so the value of m, it ranges from 0 to 1. Now, here Brooks and Corey, they have given the value of m, that is MBC, it is greater than 0, and that relationship is given like this. K by Ks is given by this, and then that is the range for the effective saturation. So, these forms of the models are convenient to use when the unsaturated movement of water takes place to the soil. Now, the Darcy's law, it is a famous law, and this law states the flux density, it is given by the flux density nothing but the Darcy's flow, which we call it as the velocity of flow, rather we can say, which has a dimension of L t to the power minus 1. So, the Darcy's law states that it is given by the JW, it is the flux density is given by minus K, that is hydraulic conductivity, into the gradient of hydraulic head, and this particular hydraulic head is nothing but it is the sum of the pressure head plus elevation head. This particular law is meant for flow through porous media when soil is under saturation. So, this when it is the water movement, it is taking place vertically downward direction. So, we put it H equal to capital H equal to H minus Z, which is Z is positively downward direction. Now, since Darcian velocity JW, it is in a vector form, because what you are seeing this arrow, this is in the vector form. So, components of the this particular Darcian velocity, it in x, y and z direction can be estimated. So, Darcian velocity Jx equal to minus k delta h by delta x. Similarly, in y and z direction, this can be estimated. So, Darcy law is empirically based, and it originally derived for saturated flow. It is a constant and saturated flow. Means this is, but now Darcy law is also extended, where k is taken as a function of theta. Now, Richards equation, it is used, it is a continuity equation that is used for unsaturated flow. So, mass conservation of water flow, it is given by the moisture content with function which is a function of time t. It can be given by divergence. Divergence, this is your velocity vector, that is the j w plus a. So, divergence vector means your of j w, it, and then a refers to the source or sink. So, in the term when we say the source means when there is a water it exists, and then water when it is taken out from the source, it is the water uptake by the plant root system. So, expressing the flux J w by means of the Darcy's law, it leads to the unsteady state moisture content is given by divergence of k grade h plus a. In Cartesian coordinate, this particular equation 8, it can be written in x, y and z direction. So, this is given by delta theta by delta t. This can be written, this is for the when the means we are expressing in x, y and z direction, including the sink or source term. The alternative form of the Richer's equation, it can be given, that can be given in terms of diffusivity. So, diffusivity d equal to k dh by d theta, means h is a function of theta when we are differentiating, that can be given k by c. So, c is the specific water capacity, it has a dimension of L to the power minus 1. Now, some alternative form of the means Richer's equation, which is in one dimension, it can be given in terms of the in terms of moisture content. So, del h by del t, this is the one dimensional equation which is given by del by del z, and then diffusivity into the change in the soil moisture content in the vertical direction minus hydraulic conductivity, change of hydraulic conductivity with respect to z. Similarly, the same equation it can be written in terms of diffusivity, or it can be also written by using the expression for steady state case, that hydraulic conductivity k equal to saturated hydraulic conductivity exponential multiplied by L phi to the L phi into h. L phi is the soil parameter, h is the pressure potential, and in the quasi linear form this equation, that is given by del square phi minus alpha del phi by del z equal to 0. This is for the steady state condition, here unsteady state. So, for steady state condition this equation has been put up in this form. So, soil water modeling under drip system, here we are interested to find out the models, and these models can be it can be physically based, analog based or mathematical models. And in all these cases soil water movement, when we are considering the what is the flow rate to the soil, means with the dripper, and how long the water is being supplied, and it will depend upon the what is the soil properties, and then the what is the depth of root zone and the rooting density. So, soil water interaction. So, all these part are to be supposed to be incorporated while modeling. So, these models could be physically based, analog based or mathematical models. So, one of the simple model which was developed by Shuminek et al. In 1999, that is Hydrus 2D. Initially he started with the 1D, then Hydrus 2D came, and then he has used the Van Gunsten formula and Brooks and Corey formula in developing the solution of that model. So, the volume balance approximate solution with and specialized cases of the closed form solution for the have been applied. So, the equation which I explained you there, this equation, here we are taking the steady state condition, mean theta is independent of time, and then the hydraulic conductivity is expressed as kh. Kh means it is a function of the pressure. So, which is negative pressure, means soil water tension, that is given by Ks into exponential alpha into h. It is amenable analytical solution via linearization process. So, a generalized equation for the positive downward direction, for the steady state form, it was proposed by Varick in 2003. This equation has been used, and this phi here what we are given, it is given by this equation, and which is as a that is k is a function of hydraulic conductivity, is a function of h with the integral minus infinity to h, which can be expressed, that is Ks exponential alpha h divided by alpha. So, this is the solution of this equation in terms of the integration form, and these are the parameters, and the values of this particular parameter, that is alpha. It is a soil specific parameter, which is given by this Immojager, Fad et al. 1984. He has listed the value of alpha for variety of soils. These are the some of the forms of the where the dripper is placed on the surface, where the dripper is placed at the subsurface, the type of flow when we are considering that there is a strip of, that is your line source dripper, strip of strip source water is being given or disk source water is being given. This is a 2D array of lines of 1D uptake, means water is being taken 1D part, and this is 3D approach. So, three dimensional point source with the cylindrical uptake. So, these are the steady state way of supplying water, and then the solutions have been developed considering these flow geometries. So, in the two dimensional cases such as arising around the line source, we are considering that the along the y axis, the water is taken as y axis or radial. So, y is considered in the radial direction, particularly x, y, z when we are talking. So, x and y is brought in terms of radial components. So, for three dimensional cases, the points in the radial axis is denoted by r. So, x or r, x means here x direction, that is r because it involves x and y both the components. So, source of water provides constant inflow, that is a q is the rate of, that is a inflow, that is a discharge rate, and this is the non weighted boundaries are assumed to extend to the infinity. So, for the buried point source emitter, the approximate solution given by it is given by phi 3b. This is the expression which is been alpha divided by 8 pi rho exponential z minus rho. So, z is 0.5 alpha into z, and then r is 0.5 alpha into r. So, rho is given by z square plus r square. So, these two components have been utilized to find out the value of rho. So, means rho involves the radial direction, rho involves the value of your the alpha also. So, this is one of the simplest analytical expression to the drip irrigation flow from buried source. So, in order to calculate the pressure head, we need to have the value of alpha, Ks and Q should be known. Now, the first step to calculate the metric potential. So, this has been put up at this psi equal to psi 3b, and then h is related by this particular function, that is alpha e to the power minus 1, or what we can say 1 by alpha natural logarithmic of alpha psi divided by k s. So, we are using this particular thing. So, region for this psi is large when h is greater than 0, it should be disregarded or alternative solution is sought. So, more realistic model for surface point, we were talking about when it was a buried. Now, here for the surface flow, and when the surface point emitter is given, that is the previous case. Let me just show you the diagram. This is your 2b, when the point source, we were talking about this part, previous one, and here we are talking about this part. So, this is a figure 2b, and then equation has been obtained, which in this is the equation, and this equation is to be solved by using the Euler's function, which is Euler's equation. This is the Euler's equation. So, Euler's equation, because this particular thing can be, this particular integral can be solved by using the Euler's equation. So, this has been obtained. Now, here the two cases, one is the when the drip emitter is placed at the surface, and then another case is drip emitter is placed in the subsurface case, and then the flow rate for the surface case is 1.19 into 10 to the power minus 7 cubic meter per second, and in another case that is your subsurface case, the amount of water, it is 4.44 into 10 to the power minus 4 liter per second. So, and then this is the another saturated hydraulic conductivity is given, and the value of alpha is also given. So, then these soil moisture movement, the data soil water movement, these are the for different time, the values were obtained. These are the values which has been obtained. The contour become elongated vertically, showing the effect of gravity at the distance pressure from further it goes out. So, this is the way how the soil water distribution takes place when there is a steady state flow. For surface ponding, in case of this steady state flow for surface ponding, Bressler has obtained the solution where R naught can be estimated by this equation 20. So, here again you will find that the R naught is the radius of ponding, it is not the total radius of this is the radius of ponding, and this radius of ponding can be estimated by using this expression. It will increase with either increasing the flow rate, that when the discharge Q is increasing, means you are taking the higher discharge rate drip emitters, or decreasing the value of the saturation, or decreasing the value of the means saturated hydraulic conductivity. So, one can find out the radius of ponding when we are considering the line source. So, for line source, the means your particularly line source, it is we are considering as if it is a buried dripper, or it is a inline dripper which is buried below the ground level to a certain depth, and then the equation for the movement of water or hydraulic potential, it has been obtained. And now, here this in this particular equation, if you see k naught x square plus z square, k naught is nothing but this particular function, it is a Bessel function of the second kind. So, we will be using the Bessel function table to substitute the value for when we are finding out this. And then in case of unsteady state K, to capture the dynamics changes in the soil water associated with the initial wetting and intermittent irrigation, the redistribution, the transient linearized form of Richard equation is used. So, this is a general equation of the water movement through the drip emitter, particularly for unsteady state flow. So, this is given by the change in the soil moisture content with respect to time t, that is delta theta by delta t, is given by the this is your hydraulic conductivity function, and this is the soil water function, and del square phi, this is the second order derivative of phi, means we can write here del square phi by del x square plus del x del square phi divided by del y square plus del square phi by del z square. So, this is the gradient square of this one minus k delta phi by del z when we are considering the vertical movement, where k is the means small k, it is a function of delta theta, means it is the first, means it is a function of theta, means k moisture content. So, this critical assumption limits solution applicability to narrow increments of water content change within the soil volume. So, when we are considering unsteady state flow case, you can see how the metric potential it is changing. Particularly, we have been given this data, means we know that alpha is known, and then Ks is also known, and this k is also known, which is given by these values. And for the r, means this is your radial direction when r equal to 0.1 and z equal to 0.1. So, the symbol here the triangular symbol, this is the case. So, up to this part you can see how the with time the metric potential of the water movement through a surface drift system, it is changing, and after certain time it becomes your steady. So, here from this point onwards, after 20 hours you see this has become almost steady state. Similarly, for the when r equal to 0.3 and z equal to 0.3. So, the for other the this particular graph which you see, this is the graph which is available for other cases. This is for surface drip, when the dripper, means point source dripper, is placed above the soil surface, and when the your line source drip emitter, it is buried below the ground level, how the metric potential with time it is changing, when these are the constant parameter which are available, and then these cases when we have the prediction has been made. So, when it is fitted, so these values for the r equal to 0.3, z equal to 0.1, r equal to 0.2 and z equal to 0.5 and r equal to 0.2 and z equal to 0.5. So, for different time interval how the metric potential it is changing. So, we can compare the of course, Ks is different, this is Ks equal to 0.49, this is, so this is half of the Ks. You can see here the alpha is also different and k, small k is also different, but what we see here that the how the metric potential with time it is changing. So, measured and calculated value of metric as a function of time for surface and the buried source at 0.3 meter, it is shown when initial soil water content is 0.18 and then the rate of flow we can say or discharge of the dripper is 1.6 liter per hour. This is the developed by Coelho and OR the 1997. So, these are the references to go through the more deeper about this topic, particularly when the soil water content it is changing with respect to time, and also when the moisture content it is changing when the discharge rates are varying. So, we in this particular lecture we learnt about the soil water characteristic curve, sorption and desorption case. We also learnt about the soil water movement of drip emitters, how Darcy's law and Richard equations are being used, particularly for the soil water movement in case of drip emitters, quasi-linear solution to Richard's equation for steady state and transient conditions have also we have tried to learn. So, in the forthcoming lecture we will learn about design and development of drip emitter. Thank you very much.